Welcome to Hot Chips 22. Session 6, Servers.
I'm Alan Smith. I'm going to chair the next session. The session title is Servers. We've got 3 speakers, 2 from Intel and 1 from China. Actually, 2 of our speakers just flew in, one of whom will be jet lagged, I presume. Our first speaker is going to be Dheemanth Nagaraj. His co-author is Sailesh Kottapalli from Intel. Their talk is going to be Westmere-EX, a 20-thread server CPU. Dheemanth is a principal engineer based in Intel Bangalore. He's the lead microarchitect for the Westmere-EX CPU. Before joining Intel, he was with HP and contributed in various technical capacities to the Itanium family, the HP Superdome, scale-up chipsets, and PA RISC CPUs. His interests are in the areas of server CPU architectures, cache consistency protocols, memory, RAS, and scale-up architectures. He has a master's degree from Purdue and a bachelor's in electrical engineering from the National Institute of Technology in Surathkal, India. Dheemanth?
Well, guys hear me? Yep. Thank you, Alan. So like Alan said, my co-author is Sailesh Kottapalli. He couldn't make it to the conference here today. He's a senior principal engineer based out of Santa Clara here. We'd also like to acknowledge the Westmere-EX design team for building this product. Okay. So we'll quickly skip through the mandatory slides. All right, so what is it that we're going to be focusing on in today's talk? So this is going to be focused on the Westmere-EX CPU. We will talk about the baseline architecture. We will also give you a flavor for some of the key enhancements that are made on vectors that are important to server CPU design, right? So performance, power, RAS, security, and virtualization. Things that we'll not be touching upon today. So this is a product that's not shipping yet. So we will not be talking to the clock speeds, and neither will we be talking to either the performance or the power measurements. Okay. So how is this talk structured? We'll start out with an overview of the Westmere-EX architecture. We'll talk about how we build in a balanced performance scaling. Power management has been a key focus area on Westmere-EX. So we'll talk to what we have done on the supporting core idle power states and package idle power states. We will talk about a feature called double device data correct, which is the memory RAS enhancement. And then we'll touch upon some of the security and virtualization enhancements. Okay. So I'll start with a little background on Intel's CPU development methodology, right? For a few generations now, Intel has embarked on this Tick-Tock Converged core CPU development model. So what we'll be focusing on today is the 32 nanometer Westmere Converged core. And really, if you look at the different product lines, specifically across client and server CPUs, they leverage the Converged core, but how they differentiate themselves is in instantiating a different number of cores, and also in what we call the uncore, which essentially comprises of the last level cache, your quick path interconnect, system interconnect, and your memory controller, and few other miscellaneous functions like power and clock control, right? So we talked about the converged core, but at the same time, the server-specific features and some of the reliability requirements, such as SCR, are baked into the converged core. Right? Okay. So we'll start with a fairly high-level overview, and then walk our way down through some of the details. Right. So the Westmere-EX CPU is a refresh to the Boxborough-EX platform. It is socket compatible with the Xeon 7500, and this is a CPU that was shipped, I think, sometime in March this year. The CPU instantiates 10 of the Westmere-EX converged cores. It is a monolithic die, and we have 20 threads supported and all. It has a distributed shared last level cache, 2 integrated memory controllers, 4 quick path interconnects. The way it connects to memory is through a high-speed, scalable memory interconnect, and then eventually hooks up to 8 DDR channels. And with this CPU, we can support either 2-socket or 4-socket or 8-socket glueless configuration. You can also scale up to much larger systems using a node controller, right? And of course, it's built on the Intel 32 nanometer process technology. Okay, so a couple of foils on the microarchitecture itself. So in the course of this talk, we will be using some terms such as the home agent, the caching agent, and the memory controller. So the MC or the memory controller is self-descriptive. The caching agent is, in some sense, QPI parlance for the agent that injects requests, last level cache miss requests into the into memory, right? And the home agent is where all the coherency management happens. You have requests from various caching agents, and the coherency control functions are in the HA, right? So if you look at the microarchitecture, like I said earlier, it has 10 cache slices, which are, it's a shared cache distributed across 10 slices. The physical address itself is hashed 10 ways to avoid hotspots. And on every cycle, you can have up to 5 last level cache accesses happening in parallel. And the data path width to each slice is 32 bytes, which corresponds to half a cache line, right? And the interconnect itself is a ring interconnect. It's a highly scalable interconnect, and all through the interconnect, if you can see in the diagram, you do have these ring stops, and these essentially hook up the caching agent or the LLC slice or the core to the ring, right? Now we do have 2 caching agents. It's called CA0 and CA1 in this diagram in the middle, right? So the 2 caching agents are the ones that actually okay, that works. That actually proxy requests, right, from these LLC slices. So each caching agent here acts as a proxy for 5 of these slices in this vertical row, and they actually proxy the miss request from here into the remainder of the the memory subsystem, right? And this is really a scalable interconnect because you can add ring stops, add cores and caches to it, and that improves and that scales your bandwidth, right? Now, it is a scalable interconnect, all right, but what we realized is that there are some nuances that are introduced because of some structural imbalances. Specifically, this ring stop here that's closest to the caching agent, that could, because of the simplistic ring protocol that we follow, this under high utilization situations can get starved when there's a high density of traffic from these other ring stops. So we had to build in a flexible scheme to actually reserve some slots for these inner ring slots, right? And then there's a reference to, if you want more details about the microarchitecture itself, there was a hot chips presentation last year that should give you a feel as well. All right, so we have up to 120 outstanding requests per socket, and all of these, if you have a NUMA optimized workload, they could all be mapped to your local socket memory controller. We implement a QPI source Snoopy protocol, and by that I mean every read request from the caching agent snoops all the other agents in the system, right? And this is augmented by an in-memory directory, which is mainly to cater to tracking of ownership requests from the IOH, right? And the home agent itself pre-allocates up to 256 requests for a total of 512 pre-allocated requests per socket. Now on the memory side of things, we can have up to 96 transactions outstanding at memory. The memory controller itself supports out-of-order scheduling. It schedules at a rank granularity, and it hooks up, like I said, to the high-speed scalable memory through the high-speed scalable memory interconnect. And there are 2 channels that operate in lockstep, and the lockstepping really lends itself to several advanced RAS features such as single device correct and double device correct that I'll touch upon in some follow-up slides. Okay, so from a performance standpoint, we try to build in balanced performance scaling, because these servers could go into HPC workloads, could go into enterprise workloads. So outside of the traditional core cache scaling, we also wanted to scale both the raw and application bandwidth, and that was done through a combination of some scheduler optimizations in the memory controller and several microarchitectural optimizations. To touch upon a few, the number of outstanding requests in the caching agent was scaled, the number of requests in the memory controller was scaled, the scheduler, all of the scheduling resources were replicated to be able to do per rank granular scheduling. Now we have built in, and I'll talk to this in more detail, an IO directory cache to 8 HPC type applications with some which have a high percentage of non-temporal stores. And then we have a protocol enhancement that we put in that we call a directory assisted snoop flow, which I'll talk to. And then there are some microarchitectural techniques by which we were able to reduce the operating voltage, which improves your power efficiency. Okay, so what is this IO directory cache all about? Now the idea, like I said, is to improve the bandwidth delivered to the application for HPC type of workloads, which do a lot of non-temporal stores. And by non-temporal, I mean you could have a non-temporal hint that essentially lets you store directly into the memory subsystem without actually having to fetch the line into cache. And it's useful for matrix type of operations wherein there is not a whole lot of temporal locality, right? You don't want to pollute the cache. Now, what happens though is when this gets translated to the QPI coherency domain, it looks like a request for ownership followed by a coherent write back. And like I said earlier, there is a directory-based scheme, and the request for ownership has a directory lookup overhead, which eats into the delivered application bandwidth. So with this IO directory cache, what we do is we cache addresses that are requested by the IOH, and we eliminate directory lookups for these class of requests, and that essentially means that the bandwidth that you see on the memory subsystem is the bandwidth that's delivered to the application. Okay, so moving on, directory assisted Snoopy. So this is an enhancement to a directory flow, and the idea here is to improve memory latency, local memory latency for accesses in topologies that are Snoop bound, right? If you think of an 8-socket glueless platform with a source Snoopy design, each request has to snoop all the other peer caching agents. So in parallel, you go fetch data, but there are situations wherein the data comes in first and you're sitting there waiting for the snoops to resolve. So we augment the in-memory directory with a new directory state called the remote state, which tracks remote socket ownership. And so if you have a local socket request, you consult the directory and then you figure out that this line is not cached by a remote socket. You don't have to wait for all the snoop responses. You can just return data, right? And you actually save this amount of latency, right? So that you return data early, and then you wait for all the snoops to resolve, and then send out the complete. So what used to be data return coincident with the complete, essentially the data is returned early, and you save latency in these configurations. This is also useful when we scale up with node controllers where the latency might be snoop bound. Okay, so on the power management front, I'll just give you a flavor for some of the enhancements that have gone in. Now we do support the core power down state that we call as the core C6. This essentially tries to, it eliminates leakage power in the core. So when the OS detects that the threads are running idle, it can request for this low power state. We have power gates per core that can shut off power to the core. Now, on the one hand, it saves you leakage power, but at the same time, the power that's saved, if there are few cores that are active and few cores that are idle, the power that's saved can be returned back to the active cores, and you get much better dynamic turbo boost characteristics because of this, right? So the one thing that we had to deal with as we went through, this is typically the case with some of these involved power management flows, right? They interact quite a lot with some of the PCI ordering rules. Sometimes they interact with our own QPI message class dependencies. There are other global flows such as the lock flows with which it interacts. And so there were several interesting deadlocks that we had to resolve as we designed this in. So the figure on your right, if you have a burning desire to learn more, I'm not going to go into the details, but I can talk to you offline. There were some very interesting deadlocks that we had to resolve, which comes at a fairly heavy tax, having to build virtual channels to ensure that your exit transactions make fork progress and so on, right? Now, once you build in this low power core state, we also went ahead and built in what we call negotiated packet states. So what happens here is that when all the cores in the socket go to a, let's say, C6 low power state, it triggers a negotiation process with all of the other peer agents. And if the responses are favorable, that essentially means that your entire platform is idle, and it gives you the license to go ahead and take some more power management actions, right? So you can go ahead and say, okay, I've negotiated, everybody is okay with the latencies that might be incurred on some shared resources. And in this case, you'll see that we do take some, once we get into this packet state, we do take some additional power saving actions, right? And the negotiation also helps to give an early indication. So if one of the sockets gets an interrupt or one of the core gets an interrupt, while it's working through its exit flow, since there are a lot of shared resources that could get accessed, it can essentially give an early indication to the other socket and say, hey, you might have some transactions that might come your way, so be ready for it. So it kind of the whole coordination flow of negotiating and then getting into a packet C state we found was pretty powerful. Now, from a package C6 substate standpoint, there are a couple of key things I'll touch upon. Now, once a package enters a C6, what it does is that it goes ahead and puts the high-speed memory links in a low-power state. And as we know, these I/O buffers are power hungry. There are a lot of there's a lot of bias currents that draw a lot of power, right? So we put the links in a low power state, and then we also put the memory in self refresh. But there is an exit latency associated with it, and we try to optimize that to make sure that if there is a DMA request that comes in later, we don't throttle and back pressure the fabric, right? So it's carefully optimized, taking into consideration the buffering we have and so on. The second thing we do is what we call very aggressive macro clock gating. Essentially, we go ahead and all of these green labels correspond to areas of the chip that get clock gated, and the clock gating happens at the regional clock buffer level, right? So it's substantial power savings, and then there are so the cores, of course, are all powered off. There are some areas like the router that are still running clocks freely, because that is where all of the you clock gate and then you get in-band traffic. That's where it gets buffered before the clocks wake up, right? And if you have out-of-band wake-up events like a pin-based interrupt, that again is transferred to our power management firmware, which wakes up the clocks. Okay. Now RAS is a critical vector for the high-end servers that we designed, right? Now the baseline design already supported single device data correct, and essentially what that means is that if you think of it as a memory subsystem having several ranks of devices, and rank essentially is a set of devices that are accessed in parallel, right? So you can have some of these DRAM chips go bad and still recover from it, right? Now in this case, if you have a by 4 DIMM, you can have up to 2 devices in that rank that can go bad, and you can still be up and running, right? And in addition to the 2 devices that can go bad, you can have one other bit flip, right? So this essentially goes to talks to when do you actually initiate a service call, right? You have two devices that are going bad, and after that you still have, you can still deal with soft error that can flip a bit. So you have a lot of error correction capability here. And this essentially, if you think about it, a by4 device going bad with our standard DIMMs that we have essentially contributes to, because we have channels in lockstep again, right? It contributes to 16 bits going bad, and you need 32 bits of redundancy to cover it. Whereas if you have a by8 chip going bad, up to 32 bits can go bad. And so the observation here was that you can correct at a by4 granularity and a by8 granularity. And since with a by4 granularity, you get up to 2 chips that can go bad and still be up and running, right? And so this diagram here essentially talks to at high level how this is done. We start out with a good rank, right, and you have a spare DRAM to start with, and then 2 devices can go bad, and between the spare DRAM and inline correction, you can recover from it. Okay. Quickly touch upon security and virtualization. So on the security front, the code that we leverage, and my colleague who's going to present the next talk will likely go into some more details on this. The code that we leverage has 6 new instructions. It extends the ISA, we call it the AES NI set, primarily for cryptographic acceleration, right? So it accelerates encryption, decryption, key generation, and carryless add. Now, a lot of literature exists in the public domain, so you can use this link to learn about what these instructions do, and and so on and so forth. Now, on the virtualization front, we do support real mode addressing for the guest, and it essentially eliminates performance overhead due to the VMM having to interpret real mode, right? In addition to that, so you folks might be familiar with the way Intel supports VM entries and VM exits. We have a data structure called the virtual memory control structure, and with this structure, what we have done is we provide private memory on a per thread basis, private cache on a per thread basis. So your entire virtual memory control structure can be cached there, and it lends itself to improved VM switch latencies, right? So that is more or less what I had. And so in summary, we believe that Westmere-EX is a compelling refresh to the Box Pro EX platform in the 32 nanometer process generation. We've tried to focus on a balanced feature set that spans across scalable performance, like I talked about, power management, RAS, security, and virtualization. And there were some inherent bottlenecks with the source Snoop latency performance for certain topologies. There were some directory lookup overheads that we've addressed through some microarchitectural innovations. The other thing that we've done is we've brought in state-of-the-art idle power management features for the first time into the EX space. And then we've built on top of what we inherit in terms of core, the converged core security and virtualization features. So that's all I had.
Well, thank you very much. We can take a few questions if there are any. I realize that was a huge amount of information, and you may still be digesting. Sure.
Hi. I have a question on the cache structure you showed initially. You had a ring topology, or a double ring topology.
Do you want to just identify yourself?
Oh, I'm James Tringali from Rambus.
Thank you.
Yes.
So this, and you said it's shared, it's distributed and shared. Mm-hmm. So does that mean that there's a kind of a variable latency if a core misses and needs something in the cache that's
right.
There?
So yeah, we're quickly getting to non-uniform cache access kind of issues, right? Yeah, there is variable latency depending on whether the address hashes to a local slice or hashes to a remote slice. So you will see some. So we try to minimize the. So it is a bidirectional ring. and there is intelligence built into how you route, right? So you do take the shortest route, but there is a variation in the latency, you're right.
One more related question. So when something is requested from something a slice further away, does the data migrate to the requester? So for the next access, it's faster? Or
no, we do not support any such heuristics for migration. So it is on an address by address basis, it is cached in a fixed slice.
Okay. Thank you.
Hi, Charlie Demergent, semi-accurate. Nehalem-EX didn't have a directory. This one, which is sort of a variation of Nehalem-EX, does. Any reason you put it in a Tick or Tock or whatever this one is?
So when you say directory, do you mean the directory cache or the directory in-memory directory?
The directory cache.
Right. So the directory cache was, frankly, based on a observation that we noticed pretty late in the game. Like I described, it's specifically targeted at these category of workloads that use the non-temporal flow, and that specific inefficiency wasn't noticed until late in the game for Nehalem-EX to respond in. So we went ahead and put it in.
Nathan Brookwood, Insight 64. Another one of these Nehalem-EX, Westmere-EX comparisons. In Nehalem-EX, you had 8 cores. Now you're going to 10. Moore's law would suggest you had an opportunity to add a lot more cores. What was the thinking that kept it at 10?
Well, I guess it gave us our sweet spot for the performance and the time to market schedule we were looking for. So we believe that with 10 cores, it is going to give us compelling scaling.
Well, it's still very compelling, but was it that software couldn't take advantage of more cores, or?
No, I wouldn't say it's so much a software thing. It was just a design choice based on where the product fits into the roadmap and the performance level that we need to be at.
Okay, thank you.
Yeah, I have a question.
Please identify yourself.
Yeah, I'm Sanjeev from Oracle. In your case, when you support C6 states on the cores on the ring, did you make any special arrangements in the coherency protocol to mitigate the response from a particular slice? Like if you are doing an invalidation to another cores, at that point that core is in C6 or something like that, and it needs to invalidate its primary caches, so that will deteriorate the response time for the other cores. So
no, when we do a C6, we actually flush the mid-level caches in the core. So
what about the
you would never have a requirement to actually snoop. You could have stale state that could cause you to snoop it, but you do flush the caches, and you don't have to wake up the core every time you need to respond, right? You essentially, because the caches are flushed, you can spoof a response.
That holds true for the for the other socket which is trying to snoop out the data from this particular socket in which one of the cores is in C6. So that address has to be blacked out for that particular cache, or how does it work?
So if I understand your question right, you're saying you have on the socket, you have one core in C6, maybe another core is active.
Right.
And then you have an access from the other core, but that can never be cached in the core that's in C6 because the local cache in the core is flushed before you enter C6.
Okay, thank you.
Yeah.
Okay, thank you. Thank you very much. Okay, our next talk is also going to be from Intel. It's entitled Architectural Innovations in WSM-EP. There are 7 authors listed: Muntaquim Chowdhury, Bachand, Dave Hill, Erik Hallnor, Barry Huntley, Brent Boswell, and Rajesh Parthasarathy. Our speaker is going to be David Hill. He's a senior principal engineer in Intel's Oregon CPU architecture team. He's the lead architect of Intel's first quad-pumped bus logic microarchitecture for the Pentium 4 products. He was the lead architect and concepts architect of the Nehalem and Westmere Uncores, lead architect for Westmere. Was a student at the University of Minnesota, and has had 30 years of computer design, validation, and architecture, including big iron machines prior to joining Intel in 1993. David?
Thank you. Okay, so today I'm going to go over a little bit on, again, you've heard this Tick-Tock thing probably 1,000 times, so I'm going to skip that for the most part. But I will try to give you a, oh boy. Okay. I'll give you a little bit of a sense of why I actually like this Tick-Tock model, and then we'll go over some of the focus areas for the Westmere-EP part. Again, EP, I guess that's probably a marketing term, efficient performance, I think, as opposed to the EX machine. This is the smaller core count server machines, as opposed to the EX that you just heard about. Okay, so a couple of things on the Tick-Tock thing. So one of the things I really like about Tick-Tock is it balances the risk. So, you know, again, I'm in the implementation side of what Intel does with the architecture team. We work very closely with our design and validation partners. Part of what Tick-Tock does is spreads out our risk profile. So on the TOCs, we do the heavy architectural changes and new platform and so on. So for Nehalem, that was where the QPI links, the on-die memory controller, the uncore concept got put together, this modular structure that we separate cores from uncores. Talk a little bit more about that in a minute. But then when you get to the ticks, where there's a lot of risk associated with bringing a new process online, we do less architectural work at that time because there's going to be so much what I call team oxygen that needs to be devoted to dealing with the conversion of the TOC architecture to the new process. Okay, so the challenges, the ticks, so the design team would say these are developed in a very constrained environment. The TOC team itself is very busy delivering the prior art, I would call it the Nehalem generation of products. The execution teams are very busy dealing with that product and getting it out to market, getting the issues sorted out with the customers and getting that thing to full production. So when it comes around to executing the ticks, in the past Intel either needed to get a different team on, ramp that team up, or as was done with the Nehalem Westmere program, the same execution teams actually delivered Nehalem and Westmere. So we got a huge advantage from being able to use that same team that had all the mind share, but they were very constrained in time because they were busy delivering the TOC product, and therefore when the tick comes around, the timeline is short, and of course at Intel, rule one is you don't hold up a brand new fab from shipping products. So the other things to deal with in this constrained environment, the process stability. Since it's a new process, there's quite a lot of back and forth that goes on, defining metal pitches, the strength of the transistor drives, and so on. There's quite a lot of back and forth that goes on between design, process, and architecture to actually convert a TOC program over to the new process and implementation, because there are quite a few different, the new process typically looks different than the old one did for a number of circuits that behave differently. Okay, other big thing, again, this is just in terms of philosophy. There's a great desire to maximize the leverage of the existing design database that's being used, that which is inherited from the TOC. Typically, we're trying to get about 60% reuse. And that's not just RTL reuse. They can actually, what's called P-shifting, there's a semi-push button process of being able to move individual circuit regions from one process to the new process. And then of course we work out the detailed issues there, but quite a lot of the logic, we're trying to move it directly from the old process over to the new process. So Westmere was a little bit higher than 60%, but we like to use as much transistor layout level reuse as we can. So obviously to do this, you can't be doing wild gyrations, which is why we like the lighter weight microarchitecture in the new parts. And of course, this isn't just an Intel thing. For every OEM who has to requal these systems, the more stuff we throw up in the air, the harder it is for those OEMs to get confidence in their systems that they're really production worthy and ship them. Okay, so what is the Westmere? Again, this is I think the product name is 56xx. I'll mention this is all shipping product I'll talk about today. So you're looking at a couple of die plots here. On the right-hand side of the diagram is, left-hand side is the Nehalem product. So that's a 4-core die plot, 263 millimeters. These die plots are roughly to scale here, actually. So the new part, you can notice obviously the 6 cores in the yellow boxes there instead of 4 cores, and a corresponding amount of cache that's slid upside the cores there. There's 2 megabytes of cache per core slice there, although it is a fully shared cache. Okay, so key point here, drop it into the same socket. Part of what we were looking for philosophically here was to be able to follow up the Nehalem program with a set of the new process products that just drop right into the socket with as little perturbation as possible. So you need a little bit of a BIOS change, but if you built platforms to the Nehalem specs, which pre-identified issues we were going to face with moving to the new process, then you should be able to drop in this new Westmere part into the same socket and go. So conceptually very simple, 50% cores, 50% cache, and it shrunk about 10% in area overall, and similar total power and thermal characteristics to the Nehalem it replaced. So this is very key to the concept of what we were trying to accomplish here. It had to fit in the same thermal envelopes with the power supplies, the voltage regulators, all that stuff had to be so we could just drop it in and go. Okay, so here are the kind of high-level focus areas. We talked again about the straightforward scalability portion of this. Leverage that 32 nanometer process to grow the core count and the L3 cache. We were trying to get as much as we could out of that new process. So a 50%, again, you'll see in a minute, you don't ever get that directly, the 50% scaling from a performance perspective, but it was pretty good, nice, simple product. Loved it. Ease new product transition pain for the customers, not just an Intel thing. And 2 things we tried to accomplish here. We could give the customers the choice with the new SKUs for Westmere to either leverage that new process goodness as more performance at similar power envelope, so that's the 6 cores in the cache, similar power envelope to what Nehalem had done previously, or if you want to, you can go with 4 cores, or there's a 6-core product too, where the frequency was dropped, the voltage is dropped a bit, and you get a power advantage from it. Okay, other item, we don't need to tell anyone about security issues with the PC platforms these days. Intel's trying to take a step forward on that, so Westmere put in the AES Encryption and an extension that covers BIOS and firmware in this complicated topic called TXT. That's the Trusted Execution Technology. That's a mouthful even for me. I'll talk about that more in a little bit. And then virtualization is always a key item for the data centers, cloud computing, and so on. So we did a little bit to boost the virtualization performance. And again, there's creative people. There was approximately 100 additional incremental improvements I won't discuss today, but I'll give you a little bit more here on this next slide. The top 10 improvements. So we talked about the core and cache additions. The other item was to work on the DDR memory power. So support has been added for the 135 volt low voltage DDR3 standard. And also Intel bumped up the capability a little bit on the 2 DIMMs per channel cases. Cases where Nehalem had been spec'd at 1067, Westmere moved those up to 1333. Okay, other item was to add a little bit more buffer depth to the memory subsystems. In particular, the I/O, we had noticed we slightly underspelled the amount of capabilities we were given to the I/O channels. So we bumped up the buffering that allows more transactions in flight to main memory of the dual sockets, and in particular, that's being a portion of that's being given to the I/O subsystem. Okay, then I'll talk a little bit about these in a moment here. The AES new instructions mentioned in the previous talk as well. This trusted execution environment. So key thing that was added, trusted execution has been around previously, but Westmere closed up some issues in the hypervisor, BIOS, and rootkit attacks area, and that topic, unfortunately, was over an hour in itself, I realized, to even describe it. So I think the foils for that are kind of in the backup. There's some material on Intel's website, or you can get a hold of myself or Dr. Allen if you want to get more information on that. And then the other item is the virtualization support. 4 other items, I'm not going to hit these at all today, but the larger page size support was added for the high performance HPC apps, which have the very large memory footprints. They like a little bit larger page size. PCID is ability to reduce the thrashing of the page tables if you're context switching frequently. And then a couple items, the BIOS guys have been begging us for years to get a couple more MTRRs put in place, so that was done on Westmere as well. And then an item with the APIC timer that used to have a little time warp issue in the past, that got fixed up. Okay, so how was it done? The key point here, most of what enabled what we did in Westmere was actually done in Nehalem. So the architecture for this machine, we were thinking ahead when we did the Nehalem product to put in the support capabilities in the platform. The VRs were spec'd to handle the voltage ranges that we expected and the ability to move the voltage ranges around. I'll talk about that in a little bit, how the PCU, the power control unit, is actually dynamically moving the voltage of these parts around. And in fact, these parts all run at different voltages with respect to one another. Even the same SKUs, they run at different voltages from one another. That's part of the way that Intel was able to get this 50% extra capability into the same socket. Okay, so the pre-plumbing was done for 32 nanometer in the platforms ahead of time. So if you built to the Nehalem specs, the specs that came out for a Nehalem platform, there was some stuff in there that maybe didn't make sense why it was in there. It was for Westmere. Okay, the other item, when we were architecting the Nehalem Uncore, QPI and DDR headroom, I know there was articles that came out when Nehalem first came out with the 3 DDR channels that it looked like there was excess headroom in there. That's why. We did that and are using that up obviously on the 6 core parts now. The cache tag bandwidth, the QPI capabilities that are in place here, all of that stuff was again, at least architected in mind with that we might go to 6 or 8 cores in the future here. And it ended up at 6, obviously. Okay, another key point on the, note the boxes there. The yellow boxes are the cores. And the key point that was, part that was plumbed in during the Nehalem phase there was that those cores are encapsulated, if you will. They're completely standalone so that we could add or subtract them. You saw the EX program in the past. We're all using the same cores. The client parts are using the same core. So see if I can point at this a little bit. The rate here is the voltage frequency jump between cores and uncore. It happens right at each of these core interfaces here. The cores are sitting in their own voltage domains, and the core voltage and frequency can be moved around with respect to the uncore. There's a skew tolerant interface in there that's still low latency. That's how we jump back and forth between the domains here, and we can therefore move the frequency of the uncore up or down in the Nehalem products or in the Westmere products as needed for the bandwidth capabilities. Okay, upfront work with manufacturing. Again, a great portion of what happens on the TIC is this upfront work to try to get the metal pitch and the transistor design characteristics so that we can easily move move to the new process or as easily as possible. And then from there it plays out as the core team is set off to build the 32 nanometer Westmere core. Again, that Westmere core actually introed the 1268 process fab, the 32 nanometer fab for Intel in the client parts. But we were all using this same part, so all that we needed for the EP and EX servers went into that client core so that it was ready when these parts came around. In parallel, there's an uncore team that went off and did the extended buffering to move the crossbar. So maybe the uncore has not been described in public well before. There's a crossbar in here. It's a complex buffered crossbar, but it's different than the ring topology that was used in the EX machine. This is simple brute force, but it is an intelligent crossbar with quite a sophisticated set of schedulers in it, and it's simultaneously operating the QPI core-to-core interfaces, the cache. It's all simultaneously in operation there. Okay, so part of what was done here, again, this is the design team. You notice the cores 1, 3, 2, and 4 slid outwards. Why in the world did that happen versus tacking these 2 cores on the outside? That's design implementation issues. The designers had identified a means of saving effort, and when they put in repeater banks and things like that take a great deal of effort in the cache hierarchy. As we built this thing out, it worked out best to arrange the cores in this manner. Other than that, a lot of 2-bit fields that needed to be moved to 3 bits, and that sort of good old-fashioned hard work. But it was fairly straightforward, actually, on this part because we had thought ahead on how to get here. Extending the L3 cache, so there's a little bit of arithmetic that needed to change in this crossbar here that does the arithmetic decisions on how to go amongst these cache blocks, and it's calculating addresses underneath the cache access for going out on the QPI links and to which banks of which portions of the memory controller. That needed to be changed to a non-power of 2 arithmetic there. Okay. The rest of it, there was clocks that had to be added here because of the additional physical distances. Again, this part is slightly smaller than the old one, but when you talk about the movement to the new process, the RCs and so forth, don't scale perfectly, so there was clocks that needed to be added, and then we talked about the buffering that needed to be added. And then last part I hit here is there's a great deal of effort that goes on with the manufacturing team. After all of the design is done and we've got this part, the manufacturing team just does a phenomenal job at Intel figuring out how to bin and tune up these parts. And as I mentioned, they don't actually even run at the same voltage. They're tuning the voltage for the leakage and the characteristics of each of the die as they come flying through the fab there in order to make these parts fit into the drop-in philosophy we were trying to accomplish. Okay, so I'm not, this is a bit of an eye chart here, but I just wanted to hit how did it fall out here? So these were the 5,500 parts from the Nehalem generation. The frequencies on these are all 4-core parts, 95 watts. So these are 6-core parts hitting the same frequencies as the previous parts did at 95 watts. Here's the parts where they offer a little bit more if you want to go to 130 watts. On them, so you can get more frequency if you want to, and even a little bit more. These have dropped to 4 cores, so they're 6-core parts. They've got a couple cores fused off in order to get max frequency if you want that. And then the other side of the coin, there's these lower power parts. So these moved a little bit in frequency, so they get a little bit more frequency. Notice these are 4-core parts, not 6. But you can get these parts that have dramatically lower power in a 4-core if you like that, if the customer likes that better than the 80-watt versions from Nehalem. And then this is the 6-core part here. I really like this one, 60-watt part. Again, you pay a little bit here, but you know, fairly significant drop in power capability and yet very good performance on these. So here's the performance chart. Again, I'm not going to go through this in detail. I don't have time. There's a whole bunch of material out on the website at Intel, and I think the various magazines are writing up as well. But just, you know, can we still do good old-fashioned dumb scaling, if you want to call it that? this part turned out pretty well. There's, on the bandwidth sensitive apps, there's the boost that we talked about on the memory channels, which is mostly being shown here in the stream, a little bit on cache. And then in this, at the other end of the spectrum here, there's some of the apps where, again, they picked a part here. This is the 3.3 gigahertz part versus a 2.93. So some of this is frequency, but not a whole lot of it, actually. I think the parts, I've seen the charts already for the parts that do not have the frequency, and there's still very good scaling on those. Okay, so hit security. This is the AES new instructions. So a little bit on why not a CISC operation instead of doing AES. So there's the 3 different key sizes that are standard in the AES support. They take 10, 12, and 14 algorithm rounds in the implementation that Westmere has executed here. Again, I don't know ECB, CBC, CTR. I'm not the expert on that, unfortunately. But there are a large number of modes here is the point. So rather than building a CISC type instruction where Intel tries to guess exactly what the industry wants to do, what was done was split this AES into a number of component instructions and let the people doing the encryption work in the industry use this to their best advantage. So these are the 7 instructions here. I've listed the 6 AES instructions, and this careless multiply is also used by a couple of the vendors. Again, there's white paper on this out at intel.com. So here's the flow. Again, I'm going to buzz through this quick because I'm going to run out of time here. But the encryption flow is basically a generation first round. Then there's this N rounds we talked about, and then the last round is the AES encode last, and it goes upside down to do the decode on that. The flow looks very similar. So here's the performance of that instruction. So you get about 8x the cycles per byte of raw improvement out of this. So there's a chart there that's showing what OpenSSL 1.0 performance looks like, and there's a fairly substantial advantage. Again, this is just showing a raw component of what is protecting your information out in the real world. I'll hit that a little bit on the next slide here. So web banking workloads, again, these are vendors that Intel is working with. This is performance data from some of their applications, 23% improvement. Some of this is 6-core capability, of course, but the AES encryption is showing substantial aids to these applications, and people are finding out that they can leave the encryption capabilities on the machines where in the past they could not, and still get better performance with these 6-core parts. Other item was the VTX improvements. So this is the virtualization technology. There was a transition latency. You can see Intel's been kind of nicking away at this over time. Penryn, Nehalem, Westmere did another improvement, which is the virtual machine control structures. We're caching those on die. Up to 3 of those can now be cached in portions of the on-die SRAM resources in order to improve the transition latencies there. And then Intel also put in support for the unrestricted guest mode. So again, there's improvements on VMmark. Again, I think somewhere between 3 and 10% of this 42% improvement is from the virtualization improvements. The rest of it that's shown lumped in here as 6-core versus the old Nehalem product. That's the 6 cores and the cache and so on. Okay, so summary on this. Again, from my point of view, I love the fact that a team that's working the TOC and the TIC together can think ahead and plan out how they're going to get into a TIC. And this modular architecture that was put into place really allows us to do some scaling for these server parts that we were unable to do or took extreme heavy lifting in the past. And a lot of server parts in the past, the cache size got bumped up or something like that. These parts are moving to significantly improved number of cores and cache capacity, and able to even sit in the same power envelopes. So that's what I've got for today on EP. Again, very pleased with this, and would like to acknowledge the team. This was not an architectural thing. I mean, we did our part at the head of this product when the Nehalem family got put together, but the design team and the validation team that put this together and the manufacturing people just did an outstanding job. This 32 nanometer process is just looking beautiful. Questions? Sorry. Oh, yeah, go ahead.
Sure, Nathan.
Thanks, Dave. You mentioned that this was the first time Intel had used the same team for the Tick and the Talk. Do you think that given the success of this program, that's going to become a best-known method inside Intel?
Yeah, and in fact, maybe I should correct myself if I said that. I'm not certain this was the first time they've ever done that. It's the first time I've seen it done, at least to the degree that it was done. And I can't speak for Intel on that topic, but it worked absolutely beautifully, in my humble opinion. I would not at all be surprised if Intel continues that. Yep.
Thank you. Good presentation.
Thank you.
Yes, go ahead.
Just in time. Carl Hewitt, MIT. Can you use QPI to connect together two Westmere chips? In which case, in terms of the memory coherence, what kind of latencies do you see going back and forth?
You're asking, do the chips connect themselves with QPI in the Westmere-EP?
Yep.
Yeah. In fact, so that's one of the differences between EP and EX. EX allows scaling to quite a number of sockets. EP is limited to the DP configuration, dual socket. And the latencies for this Westmere part are about the same as what they were in Nehalem. There's a couple clocks that are added each direction for this bit I talked about of the additional scaling. But I think, as I recall, they're somewhere in the 50 to 90 nanosecond range is what the memory latencies were.
And things like lock, compare, and swap will work across that.
Yeah.
Fantastic. Thank you.
Okay, well, thank you very much. Obviously, the thanks at the end, as you all know, of course, all of these products are, in fact, a cast of hundreds. And so when you see 2 names or 7 names on the talk, that's only a small dent in the list of contributors. Our next talk is going to be Weiwu, who's going to be speaking on the GS464V. This is a Godson processor. It's a high-performance, low-power XPU with 512-bit vector extension. Weiwu received a BS degree in computer science from the Department of Computer Science and Technology, University of Science and Technology of China, Hefei, China, in 1991. He received his PhD in computer science from the Institute of Computing Technology at the Chinese Academy of Sciences in Beijing in 1996. He's currently a professor at ICT. His research interests include high-performance computer architecture, parallel processing, and VLSI design. Since 2001, he's led the Godson, otherwise known as the Lungsong, project to the National General Purpose Processor of China. And he's also a representative of the National People's Congress of the People's Republic of China. I think 1 or 2 years ago we had a Godson talk, and it was such a hit, obviously we have an encore.
Good afternoon. Today I want to introduce a new architecture called XPU. What means XPU? We try to put a CPU, DSP, media processing unit, and a GPU in one core. So my presentation includes 3 parts: background, the XPU architecture, and the Godson chips based on this XPU. So in background, I will prefer to introduce CPU designs, CPU plans in China. So this started from HPCs. This is the top 10 HPC in 2008. Here, China is number 10 at that time. Then 2009, November, we are number 5. 2010, June, we are number 2. What's next? number one. No, United States will be number one. We do not want to be number one. But we want to build HPCs with domestic designed CPU. In the following year, at least 2 or 3 petaflops HPCs will be built with our own CPU. We have a CPU plane in China. Design CPU for HPC is only part of the national science and technology major project for CPU. We have, in the year of 2005, we started national midterm science and technology plan. It lasted from 2006 and 2020, 15 years plan. It focuses on 16 major projects. Each fund US dollars 5 to 10 billion US dollars from 2006 and 2010, even more. And I list some major projects. First is CPU and OS, VLSI process technology, next generation wireless network, high-end data machine tool, advanced nuclear fission power plant, water pollution control, large aircraft, high-resolution Earth observation system, manned space flight and lunar exploration. We have 16. Among them, CPU and OS is number one. So according to my understanding, our CPU plan should be in we have several 5-year plan. In the 10th 5-year plan, which lasts from 2001 to 2005, we start up and we try to do some key technology research. At the end of 2005, we attach 4 issues out of our architecture, 1 gigahertz. And now we are in the 11th 5-year plan. It's from 2006 and 2010. In this plan, the whole plan is from innovation to innovation, from low end to high end, and from research to product. We have a multiple core CPU with leading performance, and we will set up a CPU company. Desktop, servers, and HPC products will be developed based on domestic design CPU. And in the 12th and 13th 5-year plan, we should build a new ecosystem to support the IT industry in China. And the ecosystem should start from some areas such as national security, education, e-government, and so on. Gaosan CPU, we started research in the year of 2001, and we have Gaosan 1 in 2002. Then after that, we have 2B, 2C, and 2E, each triple the performance of its previous one. All of them are prototypes, none of them are products. So, but at the end of in 2002E, we reached the spec CPU 2500. Then we start product stage. We have a low end and high end roadmap. Here's a high end roadmap. We start from 4 core, and then we are designing 8 core and then 16 core. Here's the Gaosan 3A. It's a 4 core chip. 1 gigahertz, 65 nanometer, 425 million transistors. It implemented 4 core. It's 4 issue core. And 4 megabyte level cache, 2 DDR3 controller. The architecture of the chip is presented in Hot Chips 2008. Low end, we want to integrate the computer in one chip. Now we are at a 2G stage. It's also 1 gigahertz, 65 nanometer. Use a single core and some interface. The core used in Gaosan 3A and 2G we call the Gaosan 464, which means 4-issue 64-bit CPU core. It's a typical or standard 4-issue CPU core, MIPS 64 compatible, and 4-issue 64-bit superscalar out of order pipeline. It has 2 fixed units, 2 floating point units, 1 memory unit, 64K byte I cache and 6K byte D cache. both four-way associated. We have a TLB, we have a direct base key coherent protocol, we have a direct in support in the level cache, and so on. This call is, as I said, adopted by Golang 2G and 3A. It's this architecture. We can see here the branch target buffer, branch header table, and so on. Regular naming, fix in checking queue, and floating point in checking queue, a flat stand for each architecture. Then based on this, we try to develop XP architecture. The idea is like this. When we observe from Moore's law, we are facing some walls. First wall is memory wall. The memory wall calls the architecture of memory hierarchy. Then we face POC submission wall. The result is multiple core architecture. Next, we will face bandwidth wall. When we put more and more computation in one chip, how to fit the CPU. Why we propose XPU? We can see in the CPU, we have separated data and computation. It's very flexible in programming, but it's low efficient. In GPU, we have a tightly coupled data and computation. Data and computation are coupled together. It's not flexible, but it has very high efficiency. We try to put high efficiency and flexible into one architecture, which is XPU. It's reconfigurable data for computation, which means that in this architecture, we put the CPU, DSP, and MPU, everything. So if we see here, high efficiency GPU, general purpose CPU, we hope XPU should be here. The architecture features is based on 464. It keeps all 464 features and extended by each 64-bit floating point unit is to 264-bit SID vector unit. We have a dual each 264-bit SIMD, which means each core has 8 64-bit max. And it also keeps mixed 64-bit compatible. We have a 108-inch 256-bit radio file, meaning instructions. Most importantly, it takes the XP architecture. We just replace the vector unit with the floating point unit was vector unit, and added the one memory coprocessor here. So in traditional architecture, here we have a very powerful vector unit. We have vector radio file, level 1 cache, level 2 cache, and memory. This is a traditional data path. The problem is this path cannot feed the stuff in vector unit. It's very powerful, but the data can be fetched only one by one, word by word. So we have a link here from level to cache. It can transfer data continuously, 1K byte, 2K byte in one transaction, and in higher width. Sometimes even direct from memory to radio file. Even this is not enough. We should the data transfer is done in parallel with computation. And next, we reorganize data in a way from memory cache to virtual register as required by applications. Here we have an example. In a way, we transfer data from memory or level 2 cache to a virtual register. We reorganize data. We extract one port from each blocks and put them together here. We can do, with this, we call it Gaussian super link. With this Gaussian super link, in a way from memory to virtual register, or from vector register file, or from vector register file to the memory, we can reorganize data in many ways. For example, we can do matrix transposing in a way. We can do bit revert for FFT, for DSP in a way. We can also do entropy decoding in a way. So with this Gaussian super link, we have a memory access coprocessor. It do flow control along Gaussian super links and synchronize with the computation unit. So this is the idea of the XPU. The programming model is very simple. We start to transfer data from where to where and in what format. This is very important because in a way we reorganize the data. And then independent coder can be here, and we because hardware do not support dependence. So but it provides synchronization. We wait to transfer complete, then we can use the data here. So here's the example link pack. From here we do computation and shuffle in parallel, and the computation and the data transfer in here from memory or from level to cache to vector unit to VPU. And here is the memory access coprocessor. Some data from level to cache to virtual register, and some from memory to virtual register. In this way, we can achieve very high performance. Also, we do computation and shuffling in one instruction. You know, in traditional processor, computation and shuffling is doing different ALUs, different units. We implement instructions which do computation and shuffling in one. This is for FFT. There are 4 instructions. There's 2 and there's 2. And also, we have a instruction for link pack. There are only many instructions, but these are only examples. And also for media, instruction for media. The idea is to do computation and shuffling in the instruction. In instruction. And we have some previous performance results. With FPGA prototyping and RTL simulation, we found that they achieve excellent performance. In 8-core Gotham 3B, each core have 8 max, 8 core have 64 max. We only have a 2 DDR3 controller. It achieves 93% of peak performance for matrix multiplication, 87% of peak performance for 1K point complex FFT, which means with the 8 core, we can achieve 0.37 microsecond for 1K point FFT at 1 gigahertz. These numbers, as far as I know, is the fastest in the world. And with high definition decoding with single core, we can decode more than 100 frames per second with single core. The area, the size, the size over here is only this one. We call it vector DMA, which is the memory coprocessor. Here's the vector unit, vector region files, 2 vector unit here, level 1 cache, and the CPU core. Finally, I will introduce some chips based on this architecture, this core. I will introduce multiple core chips and SoC chips for local PC. This is Gotham 3B. It's taped out. Now it's in EWS tester. This is the architecture. We have it's from a scalable Gotham 3 architecture. We have a 2 node, 2 crossbar, 2 memory controller, 2 hyper-transport, and it achieves 128 gigaflops at 40 watts. We have a 2 vector unit. Here's a layout about 300 square millimeter. So this is this core. There are 8 core. Each of them are vector core, XPU core. And now we are defining the 16 core Gotham 3C. It should be 2 gigahertz, 28 nanometer. It can achieve 0.5 teraflops at estimated 20 watts. The same architecture. The K-coherence protocol is maintained with a director-based K-coherent protocol. The director is kept in the level 2 cache. Then there's a single SoC. This is the XPU, can do vector decoding, so it can do high definition media decoding. It have a GPU, DDR3, PCIe, SATA, USB, GMAC, all kinds of IOs for local PC. So there are some systems. There's a blades based on Gaussian 3A. Gaussian 3A and Gaussian 3B are pin compatible. For the systems designed for 3A can be used on also this blade. This personal high performance computer. In the border, we have these slots is for x86 CPU, AMD. We have 8. This card have 2 dual Gaussian 3 CPU and 4 slots. 8. So one x86 CPU plus 8 Gaussian 3 CPU for one box. Here's one U16P board for high performance computers. With Gaussian 3B, this 1U can achieve 2 teraflops. Gaussian 3C can achieve 8 teraflops with one unit. So, conclusion. The XPU concept is a convergence of CPU, DSP, MPU, GPU. We try to put everything together. The key issue is we want to transfer data in the way from transfer data, and in the way of calculation, we do data reorganization. And the data path is reconfigurable by the software. So it's a vector unit plus Gaussian sublink. It provides enough data with the correct format to feed the stuff in CPU, to feed the stuff in vector unit. So first is enough. Second is the correct format is very important. In traditional architecture, the data shuffling, data organization is done by ALU. Now we do it in a way from memory to the ALU. And it achieves high performance. We achieve 93% performance, peak performance for matrix multiplication, and 87% FFT for 8-core Gaussian 3B. We achieve more than 100 frames, high definition decoding with single core. And we also introduce Gaussian chips and applications. We have a Gaussian 3B, 3C based on this XPU architecture. We have a Gaussian 2H for local PC and media applications. So the XPU, the single core can be used either for high performance computers and also be used for low cost PCs. And thanks.
Erik Sharma, University of Waterloo, Cisco. Wondering your data reorganization from memory to the CPU, where exactly is it performed?
Excuse me, can you speak a little slower?
Your data reorganization between memory and CPU, where is it performed?
Oh. It is performed in here, for example, here is the CPU core. Here is the level 2 cache and the memory. It is performed in the CPU core at the edge of the CPU core. Okay. We have an AXI interface at the interface.
Okay. And is this data reorganization unit capable of transforming arrays of structures to structures of arrays? So for, and back and vice versa?
Could you speak more slowly and more simply?
Okay, is this unit, reorg unit, capable of transforming arrays of structures to structures of arrays?
Yes, we can reorganize it. It's reconfigurable. You can see here we have some radio files, multiple port radio files, so we can mix data.
Okay, and I'm curious. You said that you have some instructions where you fuse computation and permutation, or shuffling.
Yes.
So others, I believe Intel's Larrabee instruction set, they sought to fuse the shuffling and the memory operations. Why did you choose shuffling to fuse shuffling and computation?
Yes. Sometimes the reorganize in the memory core process is not enough. So traditionally, we should have 2 instructions, one to shuffling and one to computation. We put them together.
So basically, you reorganize both from the memory unit to the chip and inside the core itself as well.
Yes, it's a choice. It's a choice. our engineer like to do it here.
Okay. So when is it a better choice to reorganize in the core itself, and when is it from memory to the chip?
Yes, but something should be done in a way. For example, here are this is, in fact, is two instructions. First instruction to the reorganization, and the second instruction to this is in the registry file. Between registry file and the ALU, we also need to do reorganization. Otherwise, we cannot achieve high performance.
Okay, thank you.
Hello, thanks for the presentation. This is Jeff Howard from Intel. I noticed that the chips you were taping out in 2010 were on a 65 nanometer process, and you plan to go to 28 nanometer in 2011. Can you tell us what foundry you plan to use for that?
Now, currently we are using ST Micro,
Yeah.
and we have second source is TSMC.
And it'll be the same same foundries for the Godson 3C?
ST Micro and the TSMC 65 nanometer is compatible, but 28 is not so compatible.
Okay, thank you.
Hi, Nathan Brookwood. You mentioned that you have added 200 instructions to help x86 emulation. Can you give us a feeling for what kind of the performance you get when you're emulating an x86 on your processors?
Yes, for example, with the QMA virtual machine, native performance is only 5% or 10% if we do not have the instructions. With the instructions, we have 10 times higher speed, about 80% of the native performance.
Of the native performance of the Godson. What would that correspond to in terms of an x86 processor?
We don't have the comparison. Our comparison is, for example, for a spec CPU 2000, we compare it to compile it to MIPS, and then when compared to x86, run it in MIPS. This we can achieve 80%.
Okay, thank you.
Carl Hewitt, I noticed that you also included an x86 processor included with your Godson processors in the box. I wonder why you included the x86 in one of the configurations. What? Oh, it was AMD? Well, it was x86, AMD. I didn't say Intel.
Thank you. Oh. I'm sorry. Here is this is for personal high-performance computer. We hope in the future each professor or each PhD have its own high-performance computer. It's intercloud computing. So we have the x86 for management. It can have more run more. It's used for example for Word and for PowerPoint it can done here. Then for computation it can done here. It's for personal use. The machine is for personal use.
Okay, thank you.
Ilya Gans of Acronic Semiconductor. Since you already have a CPU, a DSP, and GPU, are you planning to make this picture complete and add a FPGA?
No, we don't have a plan to put FPGA together.
All right, thanks.
Well, thank you very much.